Welcome to the MULab's presentation on MACQ, the Model Acquisition Toolkit. My name is Rebecca, and I will be presenting this project along with Ethan Callanan. The MACQ team consists of undergrads Ethan and myself, PhD students Alison, Paredes, and Victoria Armstrong, Dr. Tathagata from IBM, and Dr. Christian Muise, the head of the MULab. What is model acquisition? In short, model acquisition is the process of taking state trace data as input, analyzing it with varying techniques, and acquiring action models in the form of PDDL domain files. To dive in deeper, we can see that the input state trace data on the left consists of a series of steps, each of which contains the action taken and the state of each fluent after the action. Here, the green indicates a true fluent, while the red represents a false fluent. Model acquisition techniques attempt to analyze patterns in the data to provide an explanation of how actions were taken and what rules apply to the corresponding domain. These rules are output as a PDDL action model, shown on the right, which describes the predicted preconditions and effects of the actions taken in the data. Model acquisition is powerful as it creates a framework for generating fully explainable planning models given arbitrary traces of actions and states, and these models can then be used to plan within the domain. Model acquisition research has been developing for over 3 decades, with no less than 43 papers in the scope and much more to come. Each technique aims to improve on the performance of existing methods or to explore model acquisition on different types of trace data, for example on partially observable or noisy data. However, the planning community is lacking a centralized place to access these model acquisition techniques for their data. Even if the code for all the techniques were readily available, no centralized API exists, which makes it difficult to flip between different techniques, quickly generate and visualize trace data, or even convert your traces into the right format for these techniques to use. This apparent gap in planning toolkits led to the creation of MACQ. MACQ is a Python library which covers the task of model acquisition from start to finish with an intuitive centralized API. First, users can either import state trace data from CSV files or generate traces from raw PDDL or problem ID. There are also a variety of trace generation methods, including vanilla sampling, which quickly generates arbitrary lists of traces, and goal-oriented sampling, which generates a trace that reaches a particular goal. Additionally, the initial state and goal can be dynamically changed in code, and the trace generator would be updated accordingly. Next, tokenization allows users to apply features such as disordered actions and partial observability to their traces. These tokens can then be passed to model acquisition techniques, which dump the results to PDDL. Best of all, this entire process can be done in only a few lines of code. Currently, MACQ supports 4 model acquisition techniques: Observer, SLAF, ARMS, and Amden. These 4 landmark papers were chosen as the first techniques to implement due to the large coverage of trace features that they support. Observer, for example, supports unmodified trace data, SLAF and ARMS work with traces with partially observable states, and Amden handles noisy data with disordered and parallel actions. This makes MACQ accessible to researchers with basic trace data as it doesn't require advanced tokenization to start playing around with it. Additionally, 3 out of the 4 techniques use set-based theories, which made them more practical to implement in tandem. Finally, we would like to emphasize that MACQ is meant to be extensible. Currently, the issue tracker is populated with more techniques to implement, and anyone is welcome to take a crack at adding the theories of their choice to the library for the community to use. As you will soon see, the MACQ API was meant to be accessible from the start. Let's jump right into how MACQ works. In this use case, the user wants to generate traces from the blocks world domain using a problem ID. To match generate trace data, they wish to generate 2 arbitrary traces of length 50, so they call the vanilla sampler generator and supply these parameters. The return trace list includes a pretty print function with different visualization options available, including the color block view, which displays at a high level how each fluent flips between true and false over time. This visualization feature is useful as a quick way to ensure that your traces are being generated exactly how you need. Now that the user knows how to generate some traces, they want to test the performance of the SLAF model acquisition technique. SLAF only works with partially observable data, which is where tokenization comes into play. The user must tokenize their traces by converting them to observation tokens where partial observability has been applied. If we take a look at the converted observation tokens, we can see that many of the steps know of missing data. These missing fluents have been assigned none instead of true or false. These observation tokens can then be directly passed to the extract class, which generates a model using the SLAF model acquisition technique. With a single function call, this model can then be dumped to PDDL. Here, the user has printed out the model, but it can also be stored in local files.
MACQ also includes an online visualization interface with the main purpose of being a centralized way to keep up to date with the state of model acquisition research. As new papers are written and new features are covered in the space, the site will be updated to reflect current knowledge. 3 visual lenses are available on the site to view these model acquisition papers. The lenses are Taxonomy, Affinity, and Network. Finally, there is a 4th tab for Insights, which provides ideas for future research. Let's go through each of these in turn. The first lens, Taxonomy, is a categorization of papers in the field based on the features that their modeling acquisition techniques require. The page includes a tree map view, which shows the agent, model, and data features at a high level, and then cascades into smaller chunks that categorize papers into the types of actions they use, fluent observability, predicate information, and more. With the hierarchy view, the user can toggle between the features that they find relevant to explore what papers might match their queries. The second lens, Affinity, is an affinity representation which demonstrates how the model acquisition papers cluster together based on neural embeddings of the paper text. In this view, each dot represents a paper, and multiple papers can be selected by holding Shift. Below the cluster is a representation of tags contained in the selected papers, ordered, colored, and sized by frequency. The third lens, Network, displays a citation network of how papers point to each other. By dragging the slider, the user can see the progression of papers through the years and how model acquisition research has been steadily growing and interconnecting. Once again, the tags below the network represent the tags mentioned in the selected papers. Finally, the Insights page uses AI to generate insights that suggest gaps in the literature. The AI generates a series of tags which describe trace features that have not yet been explored. This example suggests a new model acquisition technique that covers determinism, fully observable fluence, known noisy actions, and full traces. The AI also generates a list of neighboring papers along with their distance to the new paper in the affinity graph, and the features that would need expansion or relaxation to develop this new technique. In this example, the 2014 paper would need to add noise to its actions to meet the suggested features. The second paper would have to relax initial access to the state, and so on. To summarize, this tool serves as an excellent jumping-off point for researchers who want to get into model acquisition, as it not only generates ideas based on AI analysis of missing research, but also points out neighboring papers that they could study. In summary, MACQ is an open-source Python library that offers trace generation, trace visualization, trace tokenization, and model acquisition all in one centralized place. And then additionally, the visualizer offers a holistic view of model acquisition techniques and offers AI-generated suggestions for future research. Contributions to this project are very welcome. And finally, our call to action. MACQ is ultimately meant to be a community initiative, and it's through your contributions to the library that would allow this tool to house a rich ecosystem of new and existing model acquisition techniques for everyone to use. Remember to check out the MACQ Visualizer next time you're venturing into planning research, and finally, be sure to check us out on the demo floor.